Alternating series are awesome. Why do we care about alternating series? Well, if you're trying to analyze the convergence of a series and all of the terms in the series are non-negative, then you can break out all your usual convergence tests, the comparison test, the root test, the ratio test, the integral test. What about series where not all the terms are non-negative? So maybe I'm trying to analyze a series where this doesn't happen. It's not the case that all the terms are non-negative, but I've got some positive terms and some negative terms in my series. Well, then what am I supposed to do? Well, one thing I could do in this case is, instead of analyzing this series directly, I could look at this series, the sum n goes from 1 to infinity of the absolute values of the a sub n's, try to show that this series converges absolutely, and therefore this series would converge. And what about series that don't converge absolutely? Let's suppose I want to analyze this series, the sum little n goes from 1 to infinity, negative 1 to the n plus 1 divided by n. Now, my first inclination would be to take a look at this series, the sum of the absolute values of these terms, with the hopes that I could maybe prove that this thing converges absolutely. But that's not true. This series doesn't converge absolutely because this series diverges. What is the absolute value of negative 1 to the n plus 1 over n? This is just 1 over n. This is the harmonic series. The harmonic series diverges, so this series does not converge absolutely. So I've got to do something else. And indeed, the alternating series test comes to save the day. I'll rewrite this series like this, as the sum n goes from 1 to infinity of negative 1 to the n plus 1 times a sub n, where a sub n is 1 over n. And now what I note is that the sequence a sub n is a decreasing sequence. All of the terms of that sequence are positive, and the limit of a sub n is 0. Just the limit of 1 over n as n approaches infinity is 0. And that means, by the alternating series test, the series that I'm studying here converges. Now, I've just shown that it doesn't converge absolutely. So what the alternating series test is actually showing is that this series converges conditionally. This is partly why alternating series are so important. Well, because of the alternating series test, we can prove that an alternating series converges without using our other convergence tests on the series of the absolute values, without proving absolute convergence. We don't honestly have that many other tools for showing that a series, some of whose terms are positive, some of whose terms are negative, converges at all. Normally, the way that we'd approach those is by showing that they converge absolutely. So what are we supposed to do about those series which don't converge absolutely but do converge? What can we do about the conditionally convergent series in our world? Well, the alternating series test is a great tool in our toolbox. And the alternating series test gives us more than just convergence. Suppose I want to approximate the value of this series. Well, what could I do? It's an alternating series, so I know that the even partial sums in this case will be underestimates and the odd partial sums will be overestimates. So here's one of those odd partial sums, the sum of the first three terms, 1 over 1 minus 1 over 2 plus 1 over 3. That's an overestimate of the true value of this series. And here's an even partial sum of the first four terms, and that's an underestimate of the true value of this series. And then I could actually figure out what these are, right? 1 minus a half is a half, plus a third, that's 5/6. And here I've got 5/6 minus a quarter, that's 7/12. So I know that 7/12 is less than or equal to the true value of this series is less than or equal to 5/6. Let me rewrite 5/6, right? I could call 5/6 10/12. Makes it a little bit clearer. I think that it's actually bigger than 7/12. Now, it turns out that this series' value is actually log 2. So what I've done here is shown that log 2 is between 7/12 and 10/12. Right? What I've really done is I've shown this. Right, I've got this inequality now. But this is just coming because I've expressed log 2 as the value of an alternating series. And alternating series provide these very convenient error bounds on my estimates. I could multiply everything here by 12, and that would tell me that 7 is less than or equal to 12 times log 2, which by properties of logarithms is the log of 2 to the 12th, and that's less than or equal to 10. And then I could e to the all three of these things, right? I could apply the exponential function to all three of these things, and I'd find out that e to the 7th is less than or equal to 2 to the 12th, because e to the log undoes the log, is less than or equal to e to the 10th. And 2 to the 12th is 4096th. So what I've shown just by playing around with alternating series is this, that 4096 is between these two numbers. And I mean, this isn't great. I mean, these bounds aren't fantastic. I mean, I didn't add up very many terms in this series, right? But still, I think it demonstrates the principle that one of the coolest things about alternating series is that alternating series provide these convenient bounds for you.